So hello and welcome back. So in this video we want to do defining exponential growth. So it's basically the same idea that we have been talking about so far, but well, this is in a more formal way, specifically talking about exponential growth. So basically, if the growth, I'm just reading out the sentence that I found in the book. If the growth rate is proportional to the amount present, the function models exponential growth. So if the growth rate is proportional to the amount present, the function models exponential growth. Exponential growth. So what that means is that basically you have a function. Let's say the number of trees are exponentially growing on a field, for example, or something like that. They're planting trees based on some exponential model, and the number of trees is growing. So for example, with time, let's say this is t time in months, for example, and this is the number of trees, n of t. So for example, when t is equal to 0, you have, I don't know, you have 10 trees in that field. And then, I'm sorry, I made a mistake here. So when t is equal to 0, you have 10 trees over there. And then they are planting those trees in such a way that the number of trees is being doubled every month. So in the first month, then in the end of the first month, you have basically 10 times 2. So this is being doubled. Again, in 1 month, this is doubled. So 10 times 2 times 2. Again, in the third month, you have 10 times 2 times 2 times 2. So basically, that is the meaning of this sentence that says if the growth rate is proportional to the amount present. So basically, the amount present, for example, is 10, and the growth rate is always, you could call it, for example, in this case, the growth rate, you could call it 2. It's always this is equal to 2, this is equal to 20, and your growth rate is equal to 2. So always your growth rate is equal to 2. That means if you divide 20 by 10, you'll get a 2. Again, here you get 40 by, this is equal to 40. So 40 by 20, you get a 2. Here you get 80. This is equal to 80. So again, 80 divided by 40 is equal to 2. Or in other words, every output of the function is being multiplied by 2, and the next output is generated in that way. So that's basically the meaning of that. And here the exponential growth basically said in a formal way, defined in a formal way, is that so again, defined in a formal way, a function that models exponential growth grows by a rate proportional to the amount present, as we saw over here. And for any real number x and any positive real number a and b, so x belonging to R, and for any real number x and any positive real number a and b, so a and b belongs to R and a and b are greater than 0. And of course you know that b is not supposed to be equal to 1, that you already know, such that b is not equal to 1. An exponential growth function has the form f of x is equal to a times b raised to the power x, where a is the initial or starting value of the function. So this is called the initial value of the function, or starting value of the function. Starting value, and you know it's called the initial value because that's where your x is equal to 0. If your x is equal to 0, b raised to the power 0 is equal to 1, so then f of x is equal to a. So in that case, that basically means that where if x is equal to 0, then f of 0 is equal to a, and that is called your initial value. And b is the growth factor or growth multiplier per unit x. So I kept forgetting this and I didn't know what to call this b, and this is called the growth factor. The growth factor, or also called the growth multiplier per unit x. And this is also worth discussing, growth multiplier per unit x. And that is growth multiplier per unit x because let's say you have this function f of x is equal to a let me see, 2 times 1.2 raised to the power x. So this function, what happens is that here you have x and here you have your f of x. When your x is equal to 0, here you have f of 0 is equal to 1.2 raised to the power 0, which is equal to 1. And then your f of x is basically equal to 2, which is your initial value. And then when I increment my input by 1 unit, so again, so here I have 1.2 times 1.2 basically raised to the power 1, so it becomes 1.2, and then it becomes 2 times 1.2, which is 2 times 1.2, which is basically 2.4. So it becomes 2 times 1.2, which is equal to 2.4. And so per 1 unit of change that I made to my x, the growth multiplier per unit x caused the output of the function to be multiplied by this multiplier 1 time. If I do it, if I make again another 1 unit of change to my input, again the same thing happens. It becomes 1.2 raised to the second power, so it becomes 2 times 1.2 raised to the second power. So you can see that, for example, here I have 2 times 1.2 raised to the 0th power. So it becomes 1, and then the output is only 2. So comparing this output to this output over here, ignoring this output in the middle, you can see that for 2 units of change here, the growth multiplier has caused the growth factor to be multiplied into the output of the function two times here. So 1.2 raised to the second power means 1.2 raised to the second power means 1.2 times 1.2. So 2 times it's been multiplied by the output of the function. But again, comparing now this output to this output, when I make 1 unit of change, so plus 1 here, the growth multiplier per unit x has caused the output to be multiplied by 1.2 only once. So this is 1.2 raised to the first power. So that is basically this whole business over here. Now, we have a couple more things here to discuss, and we'll do it in a few seconds. So there is one more example here that is basically worth talking about, because that way we get to construct two functions that, that way we can also learn how to construct functions out of data. And so the rest of this is more in more general terms. We have an exponential function in which a constant base is raised to a variable exponent. So basically constant base, you have f of x is equal to a into b raised to the power x. So a constant base raised to a variable exponent. To differentiate between linear and exponential functions, let's consider two companies. So basically we have two companies here. We have company A. So this is company A and this is company B. So company A has 100 stores, already has 100 stores, and expands by opening 50 new stores a year. 50 new stores a year. So that is company A. So now, in order to model the growth of this company, you can see that the growth of this company is constant, because you already have 100 stores, and basically every year you're opening 50 new stores. So that means if let's say if 10 years have gone by, you'll have opened something around 10 times 50 new stores, so which is 500 stores, and you already had 100 stores here. So that basically means you have 600 stores after 10 years. So that's basically a straight line which has a slope. That's basically how this kind of model works. And in order to write an equation for this, all you need to do is, this kind of model is basically your f of x is equal to mx plus b. So b is basically your y-intercept always. So this is basically a function like this, a linear function, and this is going to be, for example, let's say this is 100, and then your slope is 50, so it becomes a straight line like this. Of course, it's not easy for me to draw a straight line, but it's kind of like a line like this. So basically, for let's say for 1 unit of change here, if this is 1 unit, you get around 50 units of change here. So what, it's 50 to 1, so it becomes, let's say 50, the slope becomes 50. So this kind of function is basically, you have a slope. That means if, of course we have to continue in the next video. I'll see you in the next video.